Section 3.3 is on linear independence and dependence. And one way you can think about where we're going with 3.3 and then 3.4 is about setting up coordinate systems. So you should be familiar with the idea that vectors don't necessarily have components. From a physics and engineering perspective, right, where vectors have direction, magnitude, where they're directed quantities, they're arrows, where they represent forces, where they represent magnetic or electric fields or what have you. Those quantities don't have an x and a y component until you choose a coordinate system. One of the things that you may have been told over and over again in your classes maybe is to make your choice of coordinate system clear. You think back to the inclined plane problem in physics. You can solve that problem in several ways, but depending on your choice of coordinate systems, it could be a little easier or a little harder. And your equations are not right or wrong until you choose a coordinate system. And once you choose a coordinate system, then it makes sense to break up a force vector into components. So vector spaces and subspaces, this is about vectors broadly, vectors as things. In section 3.3 and in section 3.4, we'll talk about the idea of a basis, which is essentially a coordinate system. Let's choose some directions that we can break all of our vectors into. And we have to have some sense of, well, how many vectors do we need? Which vectors work? Generally speaking, you choose a pair of perpendicular directions to do stuff in. It's not always the case. You can't always do it, and sometimes it doesn't make sense in certain aspects of continuum mechanics, for example. And in terms of eigenvectors as well. So you don't have to have perpendicular coordinate systems, though it is convenient. So we are going to be a bit more general than maybe we would in our everyday conversation. In any case, let's start. This video will be a little longer because I do a few more examples in it. So a couple of concepts. These are actually from 3.2, but they're better, I think, in this section. What's a linear combination? Well, you have a bunch of vectors, and you add multiples of them together. So here we have n vectors. If I take multiples of them, so this a1 is just some number, a2 is a number, an is a number, add them together. That's a linear combination. That's it. The span, so the span of vectors is the collection of all such linear combinations. So how much space do these things take up? Let's look at an example. So I should check that. It's my wife chatting, I'm sure. All right, I'm back. Sorry. My wife and I are trying to figure out whether or not we're allowed on campus. We're not getting any answers from anyone because nobody knows anything. Fun times. So here are two vectors, right? I hat, j hat. So what's the span of these? Well, using the definition I gave in the previous slide, the span are all of these things. So for any A, for any B, take all such linear combinations, that's the span. But that's just the entire plane. So the idea of the span is you have a couple of vectors and you ask, well, if I take every possible linear combination, what does it fill up? What does it cover? How much of space does it cover? Now these two, the span of these two vectors is the entire xy plane. Now you can have redundancy. So here are three vectors. I added one. What's the span of these three? Well, the span is the collection of all linear combinations. So it's every possible combination. But this isn't going to get me anything more than 2 dimensions. One of these vectors, this third one, is obviously just a combination of the first two. It doesn't give me anything extra. I'm not going to get into 3D. We're still just in the plane. So one of them is redundant, and it doesn't actually matter which one. We're kind of eyeing this one. It looks a little peculiar to us, but actually you could get rid of the first one. That's fine. You could get rid of the middle one. That's fine. Any two of these would be fine to span the plane. But 3 of them is redundant. It's okay. you can have three of them. The span of these three vectors is the entire xy plane. But there is a sense of redundancy here. This vector can easily be written as the sum of two others. So that's where we're going next, this idea of linear independence or linear dependence. How many vectors is too many? How do we know? How do we find out? All right, so here's the definition. A collection of vectors, n vectors, v1, v2, etc., is linearly independent if the only way for this linear combination equals 0 to be true is for all the a's to be 0. If the only way to make this thing true is for all the a's to be 0, then all the vectors are independent. So think about what this means. If there's another way of doing it, where the a's are not 0, that means I could solve for one of the v's in terms of everything else, which means one of the v's is dependent upon the other ones. It's just a combination. It's redundant. Right? So let's do an example. Here are three vectors. And the question is, are these independent? I mean, do these all point in different directions? I mean, that's a silly question. Of course, they point different directions. But are they independent directions? Can I write any vector in 3 dimensions using these three? It's not obvious to me. I can't visualize this. And so it's not hard to use the definition. Let's walk through how that goes. So I take a linear combination, right? A, B, and C. I set it equal to 0. And the question is there a way of doing this where the A, B, and C are not 0? Certainly, if the A, B, and C are 0, that works. But are there any other ways? So if we multiply the A by that stuff, and the B by that vector, and the C by that vector, and we bring it all together, we end up with a system of equations. And this is going back to chapter 2 now. So I have a system of equations. These are 3 planes. They intersect at the origin. Oh, this is just 2.3 all over again. So again, we know that ABC equals 0 is a solution, but is it the only solution? If it's the only solution, then the vectors are independent. If there are other solutions, then they're dependent. So I think probably the easiest way to do this is just to turn this system of equations into a matrix equation, and then to use what we know about determinants. So if the determinant of this matrix is, well, let's jump to the next slide. So this reasoning, I think it takes a moment to get used to. So let's work through it, and I have another example after this too. The determinant of this 3 by 3 matrix decides the question. If the determinant equals 0, then there's no inverse, which means that there are also non-zero solutions for A, B, and C. That means the original vectors are linearly independent. Because kind of going back a little bit, if there are non-zero solutions for A, B, and C, then there's a way of writing one of these vectors using the others. They're dependent. If the determinant is non-zero, then there is an inverse matrix, so we can solve this equation, and the only solution will be A equals B equals C equals 0. So the only solution is A, B, C equals 0, which means these are independent. There's no way of writing one using the others. All right, the determinant is 7. So let's go through this reasoning again. So the determinant is 7. An inverse exists. So, if you find the inverse, you don't have to. If you find it, you multiply by 0, 0, 0, you get 0, 0, 0. So the only solution is A equals B equals C is 0. So the vectors are independent. As a side note, looking ahead, if you have 3 3D vectors that are independent, their span will be all of 3D, and they will constitute a basis, which is something we'll talk about in 3.4. All right, let's do another example. This example will fail, so you have one of each. Here are 3 vectors. Again, it's hard to tell. I can't visualize whether these are independent. So I form a linear combination, right? Some A, some B, some C. We're going to turn this into a matrix equation. Now this is really actually easier than it looks. Each vector becomes a column in the matrix, right? So it's really easy to go from this first step to this second step. Once you have the second step, use Symbol Lab, find a determinant. It's 0. Now take a moment, maybe pause the video, and try to understand what this means. All right, I'm not going to pause for too long because that would be silly. So what does it mean? Well, if the determinant is 0, there's no inverse matrix. So while A, B, and C can equal 0, that is a solution. It's not the only one. If there are other solutions, then these vectors are linearly dependent. That is, one of them can be expressed as a linear combination of the others. And that is the case here. Let's be quite explicit. If you take that original equation, you do row reduction. You can use Symbol Lab for this. Just ask it to do RREF, reduce row echelon form. It'll give you this augmented matrix. And you can use it to solve for B and A in terms of C. Choose a value for C. You can notice this last row, by the way, 0, 0. So this is not an inconsistent. It will never be inconsistent. Why won't it be inconsistent? Because there's always at least one solution. A equals B equals C equals 0. So you don't have to worry about an inconsistent case. So choose a value, say C. That means that A is 2 and B is -3. And then here's an example. You can check, right? Look, 2 times -1 is -2. Minus 3 is -5, plus 5 is 0. You can check that all these sum to 0. These vectors are not linearly independent. And in fact, I mean, the way I made this example is I took these first 2 vectors and I took a linear combination to make the 3rd vector. So the idea, if 3 vectors are not linearly independent, that means one of them is a linear combination of the other ones. All right. So I'm going to, I think, pause here to have you work some problems in Top Hat, and then we'll come back together again.